approaching. X arrow, and then what was there? A number, right? Today, guess what's going to be there? Letters. Infinity. No, not letters, thank goodness. Different infinities. But first, I want to just maybe clear up something that may be brewing in your mind, okay? So, in the cases of A, B, and C, okay, we are substituting in the number that the limit is approaching right into the thing. And what would we get if we did that? If we did a direct substitution, what would we get? 1 over 0. When you have a number over 0, what's on the graph at that spot? An asymptote, right? So what I wanted to show you with this here is we have analytical ways to figure out what the asymptote would be using math, okay? So let's figure out what this would look like. Hopefully this deepens your understanding of how we can have an infinity at a specific spot versus later in the lesson when we see how we head out towards the infinities, okay? So let's look at letter A. It says, the limit as x approaches -3 from the right. Well, we know that at 3, what is this graph going to look like? Get out your calculator and let's graph him quick. What is he going to look like? Well, he's a reciprocal function, right? So he's going to have that little like, boop, look. And then he has been shifted which direction, how many units? Left 3, okay? So we have a pretty good idea of what this guy's going to look like. I don't even know if we really need to even graph it, but we will. That's fine. All right, just as we suspected, it's been moved left 3. So we've got a graph that looks like that. Now, as we head in towards -3 from the right, let's figure out what that would look like, okay? When you're envisioning these, I want you to envision a number line, okay? What is really, 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 really close to -3 on the right? -2 is kind of close, but let's get way closer. -2.9999, okay? So if we took -2.999 and plugged it into the function, what's going to happen? Let's see. This is essentially -3 from the right. So I would substitute that in, and I would get 1 over -2.999 plus 3. So do that in your head. If it was -3 plus 3, it would end up being 0, but it's not. It's just a little bit below. So what would we end up being left with? A positive? Check it out. What would we end up being left with? Think about this in your head if you can. Try to think about these in your head moving forward. But for the first one here, -2.999 plus 3. What do you got? 0.001, okay? So I've got 0.001 all under a 1. How can you change 0.001 to a fraction? Because we're supposed to be doing this by hand, right? How can you change that to a fraction?
1 over 1,000.
Okay, and then when I divide fractions by hand, what do I have? This would be 1 over 1 divided by 1 over 1,000. You keep change, flip.
1,000.
What are we approaching?
Infinity.
Yep, good job. So we're approaching 1,000, but if I kept getting closer by one more decimal point, now I'm 1 over 1/10,000, which ends up being 10,000. Then if I get closer by one more decimal point, I'm 1 over 100,000, which ends up being 100,000, right? So do you see algebraically what's happening at a vertical asymptote?
Yeah.
So we could see theoretically, using our knowledge of like fractions and stuff like that, that this guy is heading towards which infinity? Positive, okay? So this is how you could be approaching an infinity at a specific spot, okay? Now let's check out what this thing would look like from the left. So what is really, really close to -3 on the left? -4 is kind of close, but what? What's closer?
Yeah, let's do that one. How many zeros did you tell me? I forgot. 3 zeros? Okay, cool. So then now let's think about this one, but now we're approaching essentially -3 from the left, right? Okay. So now if I evaluated the function at this particular x value, I would have 1 over -3.0001 plus 3, which would end up giving me what? A negative really, really tiny decimal, right?
-0.0001.
1 over -0.0001. You guys agree?
Yeah.
Cool. Turn that into a decimal. Turn that into a fraction. Well, if this guy was 1,000, what's this guy going to be?
Negative decimal.
Yeah. All right, so now you've got 1 over 1 divided by -1 over 10,000. Now you have 1 over 1 times 10,000 over -1. What do you have now? So what's this guy approaching?
Negative.
Okay, so even though we saw the graph and we know what this guy looks like on the graph, now we've proven it with the algebra, okay? Get up. And let's confirm on the graph. As we head in the left, we're heading towards -infinity. Bertram's going down. As we come in from the right, we're heading towards +infinity, okay? So, does the limit exist at -3? And the reason is the limit as x approaches -3 from the left does not equal the limit as x approaches -3 from the right. Okay. Okay, so that is at a specific x value where the function could be heading towards two different infinities. They also could be heading towards the same infinity, right? Those are created from an asymptote. Now, let's talk about when x is approaching infinity on either side of the coordinate plane, okay? Go to the next page and think about a coordinate plane. All the way out to the right. Is that going to be positive or negative infinity?
Positive infinity.
Yep. All the way out to the left. Good job. Do you guys remember the term end behavior? You need to sign an NDA about end behavior because you're about to learn about it. So, end behavior is the function's behavior out towards the infinities. And the way you would see that is the limit as x approaches positive infinity or the limit as x approaches negative infinity. Yeah. Yeah. So there's a few different types of functions that we're going to talk about, okay? Not every function has end behavior that you can examine. For example, the square root of x. He has a clear start. Where does that graph come up? Starting at 0, right? So to the left of 0, it doesn't have any end behavior as x approaches negative infinity. What is end behavior as x approaches positive infinity, right? So not every type of function is going to have end behavior on both sides. But there are some that are worth mentioning. So polynomials. Polynomials are always going to have end behavior because they continue on in either direction forever, right? Do you guys have any sort of good tricks for remembering end behavior? I think like Krauss taught one where it was like if it's even, they're going to both be going in the same direction. This is even positive, this is even negative, right? And then I think he taught you guys if it's odd exponent, meaning like to the first, to the third, to the fifth, right? It would be like this. And then if this is if it's positive, and then if it was negative, it was like this, right? You would draw a line with a positive slope or a negative slope. Yeah? So if you had Krauss and that's how you remember it, perfect. I'm not sure how the other teachers taught it, but I have a trick that I used to teach from pre-calc if you need a little trick to remember if you don't remember, okay? Did anyone else have a teacher that taught it a different way that you remember? Okay, then you might need this trick that I'm about to tell you right now, okay? Who doesn't want to talk about penne? It's a superior pasta, delicious. So, if you write the words penne pono, and then you do 1, 2, 3, 4, 1, 3, 2, 4, I'll show you how you can use this to determine the end behavior of a
That's
polynomial.
based on,
Huh?
is it based on quadrant?
It's 100% based on quadrant,
Okay.
and then these are the pieces that you're considering, okay? E is for even exponent. O is for odd exponent. P is for positive. N is for negative. These two are referring to the leading coefficient. Okay? So here's how you use penne pono. Let's say you've got something that looks like this, negative x to the fourth. What is the sign of the leading coefficient? Negative. What is the exponent? Even or odd? Even. So I'm going to go to NE. What quadrants am I terminating in? 3 and 4. So it look like this. Okay.
Wait, so 3 and 4 is positive.
Huh? 3 and 4. Say it again. Sorry, I didn't hear you.
Quadrants 3 and 4, that would mean it would be positive 3 and 4?
No, it's saying like its end behavior, it's ending up in quadrants 3 and 4.
Oh.
So if you head out towards negative infinity, this is a good question. So as you head out towards negative infinity, what is the graph approaching?
Oh, okay, that makes sense.
Also negative infinity, right? And then if you head out towards positive infinity, what's the graph approaching? Negative infinity again, right? It's going down, going down, going down if you were Bertram. So that's how you could use the penne pono trick, okay? So let's try to use it for question number 1. X squared. The leading coefficient is what? Positive 1, right? The exponent is what? Even. So you go to pay quadrants 1 and 2, okay? He would look like this, okay? So then you use your little sketch of what quadrants this graph is terminating in or like kind of ending in, right? And you could answer any question that you needed to about the limits. So the limit as x approaches negative or positive infinity of this graph would be what? Where's the graph headed? Infinity. What about the limit as x approaches negative infinity of this graph? Where's the graph going? Also positive infinity, right? Bertram's going up. Let's try it in the next one. Yeah, so he's negative and he's even. So he's going to go to 3 and 4. So this guy's going to be looking like this. All right. So as x approaches negative infinity, the graph is going to negative infinity. As x approaches positive infinity, where's the graph going? Also negative infinity. Okay. So that trick only works for penne pono. So you can think penne pono polynomials. And then I wanted to mention a special case in number 3. So in number 3, think about the graph of sine of x. Does he have a distinct end behavior?
Sin x? No.
Right? He's a periodic function, which means he repeats in nature, right? Look at this thing. He just keeps going back and forth between -1 and 1. So what is his end behavior going to be? We call this an oscillating function. We would say that his end behavior doesn't exist.
Oh.
Because you can't say a specific value that this guy's approaching as we head out towards the infinity. It just keeps repeating. So we call this guy an oscillating function. Does not have end behavior.
Yeah,
It is
I feel
weird,
like
right?
I feel like it should be based on like what it's, like, how it's translated up or down.
What if there's a stop point on it? Like, let's say like it stops at negative. Like, let's say it's on the graph at like 3 and I'll stop at negative 1.
Well, you could put a limit at a specific number, right? You could say the limit as x approaches 1, and then you have a clear stop or start, right? You're like, oh, I'm going to go to 1, sine of 1, and then
Yeah.
if it's 1 degree, I don't know, it's like a decimal, but.
Yeah, I feel like for like oscillating functions like these, I feel like it just be like the average of the y values. So in this case, 0.
But then, like, wouldn't you be doing like the average of like a polynomial somehow? Then you'd be averaging infinities, you know?
Well,
If it never really
those aren't
heads
oscillating
anywhere.
functions.
Yeah, but like, I see what you're saying, but I don't know. You're gonna learn about something called the squeeze theorem when you go to college, and you can remember that then. Okay, it's basically saying that like if an oscillating function like this is squeezed between two other functions, it's gonna take on their end behavior.
Yeah.
So maybe that's a cool way to think about it if you want. But 4. What is 4? What type of function is 4?
Oh.
What did you say? Bad. Let's think of a more specific word than bad. What? He's a rational function, okay? Rational is ratio of two polynomials, okay? So, this is decidedly not
We
LeBron
get
James.
radical and rational functions and stuff. Just the names.
Well, radical
Like, I
functions
know
are
what they
maybe
I
more
just didn't
radical.
name things.
Yeah.
I was like, wait, no, this isn't a rational function.
Well, you gotta know what they are to, like, think about them, I guess, right? Yeah, but like, nah.
The ugly ones.
The ugly ones, yeah, they are. So what about this one, right? I have a rational function. As I head out towards the infinities, what am I really asking you about? What do rational functions possibly possess, depending on the ratio of the degree in the numerator to the degree in the denominator? Horizontal asymptotes, right? Polynomials don't have horizontal asymptotes. Oscillating functions don't have horizontal asymptotes, but rational functions do, right? As you head out towards the infinities, you're going to have horizontal asymptotes that you're going to have to think about, right? How do you determine what the horizontal asymptote is going to be? I put this little sign up here, if you guys remember from the rational functions unit. If the degree in the numerator is greater than the degree in the denominator, there is no horizontal asymptote. As we head out towards the infinities, this is growing without bound much faster than this one, therefore there would be no asymptote. You would just keep heading out towards infinity. The degree in the denominator is greater than the degree in the numerator, then we would end up having a horizontal asymptote of 0. Why? Because this is now growing without bound. We're dividing a smaller number in magnitude by a larger number in magnitude. When you take a fixed number, like a, I don't know, 1 cookie, you would examine this in your Daedalus, right? 1 cookie, you divide it by 1,000,000 people, what ends up happening to the size of each piece of the cookie that you divide? Smaller, 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 until it approaches 0, okay? And then the degree in the numerator is equal to the degree in the denominator. You just take the ratio of the two coefficients. So let's look at this guy. Yes, very good. What's the horizontal asymptote of this guy? Good job. So if I was like, yo, what is the limit as x approaches infinity of this? What would you do? Examine the ratio of the two coefficients because there's an equal degree in the numerator and the denominator, and you would just end up getting 2. Okay? Let's look at it on a graph to cement this home for you. No.
Positive even then?
That's for polynomials only. This is a rational function. He's going to be a little different. You have to use the laws of rational functions and their horizontal asymptotes. Good question. All right, as I head out towards infinity, there's 2 ways to see what the infinity is going to be on your graph. You can either use graph trace. Do you guys remember how to use graph trace, where you trace along the graph? Okay, so if you don't remember how to use graph trace, get the graph on here, and then we're going to go over how to do it again. This could be useful for answering some of the thinking questions on tests.
I was talking to Mr. Edward, and he says like the IB exam things for this class are like the ones that his kids get like the highest on. And like, what's the lowest score you had last year?
Well, it's hard to it's hard to think about it like that because
Your high
there
score
are
is acceptable.
extenuating circumstances every year, and like the one kid who got a low score like missed a large portion of the year. You know what I mean? So like don't think about the outliers, but most kids get a 5 or above. If you do your work and you pay attention, you're not just like looking at the key and you ask questions when you're lost, like you should definitely get a 5 or higher for sure. You're doing everything you're doing everything you should be doing. Are you doing everything you should be doing?
Even if you fail some of the tests.
Yeah, hang in there. Right? It's not the end of the world. So, we're on here, right? Menu 5-3. It's going to prompt you for what you want to count by. What do you want to count by, Sinjin?
Yes, Sinjin.
What do you want to count by? 100? We're heading out towards infinity, right?
Sure, count by a million.
Actually, I don't think it's going to let you count by 100. Do 10.
Count by a million.
Notice how nothing happened. You need to put the blinky dot on the graph. Menu 5-1. If you're heading out towards positive infinity, you're going to head right. I'm going right. I'm going right. I'm going right. Where's this graph going? Look at the y value. Look at the y value. Look at the y value where I'm going.
Is it 2?
Yeah.
Not really.
It's heading towards 1.99999. Keep going. We're going to get to 2. Okay? Or... or...
Okay.
You smell so God. Come on. So it's disgusting. So now you can also examine it.
What just happened?
What? It stings.
Farted.
This is an inhospitable working environment.
It's not me. I'm gonna stop you.
So now it's not going away.
I'm Galbaba, it's not me.
I don't want to talk anymore.
You might be this much, I think you're finally going crazy, Miss
I think it was schizophrenia.
So you can all, okay, it's finally going away. All right, so now you can go in the table, all right? Go to Control T. This is why I can't record my lessons. This is why. So now we're going to go to the table. Change it from auto to ask. What do you think I'm going to ask this thing? What do you think I'm going to ask this thing? Huh?
1.999.
I'm heading out towards infinity, so...
99.
Yeah. Let's do a big number. Sometimes you have an overflow problem, but... All right, where's this guy headed?
That way.
Right, so you can either do it on the graph with graph trace, or you can do it on the table. Yeah? Cool.
Sure.
All right, or you could do it algebraically with your knowledge of horizontal asymptotes. Okay, so this is me going on and on and on about horizontal asymptotes. Let's go to the rules. We are on page 24. Go to the top of page 24. We are reviewing the rational function rules, okay, for horizontal asymptotes. Are you there already? All right, so we know that if you have a higher degree in the denominator, no, degree of denominator exceeds the numerator. So now we have a larger degree in the denominator than the numerator. Can someone give me an example?
8 and a 6. Is it larger than the numerator?
X to the? Do you mean X to the? Yeah. Yes. Yeah. So the degree of the denominator exceeds the numerator. So you have something like this. Is that what you meant?
Yeah.
Perfect. So we know that this could be an example, right? Now let's use the limits. The limit as x approaches negative infinity of x to the 6 over x to the 8th. Well, you know your horizontal asymptote laws, right? What is this guy going to get to? There's one of two ways you can think about it. You could just know that it's larger over the bottom, right? So it's going to go to 0. Or you can think about it like this. I have x to the 6th over x to the 8th. What would this reduce to? Right. And then this is mathematically incorrect. You can't plug in an infinity because it's not a number, right? But if you wanted to think about it like this, I have 1 over negative infinity squared. What would end up being in the bottom? A gigantic positive infinity, right? What's 1 divided by a gigantic number? near 0, right? So we would have our horizontal asymptote. We know that a horizontal asymptote by nature approaches but never gets to 0. We would say equals 0, okay? So the limit as x approaches negative infinity of x to the 6th over x to the 8th equals 0. Whereas on the other side, positive infinity, same deal. Okay? All right. Degree of numerator and the degree of the denominator are equal. Who can give me an example?
X to the 3 over x to the 3. X cubed squared.
Can you give me coefficients so that way I can do a little division or something?
2x
Mm-hmm.
over 10.
Ooh. All right, cool. So now the limit as x approaches negative infinity of 2x to the 3rd over 10x to the 3rd, what would that guy end up becoming? We have an equal degree in the numerator and the denominator. Good job.
Bazinga.
All right. What about the last case? Degree of the numerator is greater than the degree in the denominator. Someone give me an example. Stevie! Give me an example. The degree in the numerator is larger than the degree in the denominator.
In the numerator, so in the denominator, that would be like x to the like 6th over x to the
Cool. All right, so what would happen? Well, x to the 6th over x to the 4th. What would that guy kind of cancel to? Right. And then this is an indeterminate form. You can't substitute in a negative infinity, but this kind of helps you think about what's happening, right? If I took a negative infinity and I squared it, what kind of an infinity would I get?
Positive.
A positive infinity. So where's this graph headed?
Positive.
Positive infinity. So it's increasing without bound. Therefore, is there a horizontal asymptote? Are we approaching a specific value? No. Okay. What about the limit as x approaches positive infinity? Same thing. This would reduce to x squared. And then let's plug in this thing. What would end up happening?
Still positive.
Cool. So you're telling me that, like, this guy's just going to keep growing?
Here.
Wait, doesn't an x squared just look like this? Isn't that kind of what you just found? Yeah. Very exciting. Okay. So this is all based on the way the function looks, and this is all based on the degree in the numerator and the denominator, because we're talking about end behavior. We know how to do it with polynomials. It's penne pono. What if you have something that's very creepy? And it's not entirely clear where the function is going, or even what the degree might be, right? We have the square root of something squared. Okay, this is where your computational limit laws come in, okay? Huh?
Can we just solve it? See how we did this yesterday?
That you could do it if the x was approaching a number, but it's not. It's approaching an infinity, so you gotta think, okay? So let's try to figure out what the degrees in the numerator and the denominator are. I feel like you had an idea. Huh? 1/2. Yes! Okay, so let's think about it like this. We've got the limit as x approaches infinity of 4x minus 2 over. And then St. John's like, let's take this guy, turn it into a 1/2 power, and see what's happening, okay? Now, as I discuss end behavior, I can disregard the terms that have a lower degree than the leading term. Why? Because who's going to have more bearing on this function's end behavior? If I'm approaching infinity, is 4 times infinity really going to matter if you're subtracting a 2 at the end? No, all you care about is the leading term, the 4 times infinity, 4 infinity, right? Look in the denominator. If I have a 9x squared, but then I have the square root of him, what is his real degree, the leading term in the denominator? It's really going to be the square root of 9x squared, which is what? 3x. So what I'm really envisioning here is the behavior of this guy with the degrees only.
Shouldn't you add the plus 8x too?
No, because he's really 8x all under a square root. He has a less degree than the first term. Just care about the first term. When we're talking about infinities, all that's going to end up mattering is the term in the front, okay? So what should this guy be approaching as x heads out towards positive infinity? Well, these would cancel, and what would we end up getting? All right, so let's double check that on the graph and make sure we understand how to check our answers to these. So I should type in the original function, right? And then what is the preferred method of figuring out where the graph's going towards infinity? What do you guys like better, the table or graph trace? Probably the table, right? So, oh, put them in the box over here. All right, so I'm going to ask what's going on. Where are we going? What pages are we doing for homework?
Yeah,
Yeah, it's just one page. Yep, you think about these, okay? So we should be getting 4/3. And I don't know why. Oh, I forgot the 9 in the bottom. Whoops. Do you see? I forgot the 9 down here. I'm like, why isn't it going to 4/3? All right, there we go. So now we're going to change him again. There you go, 4/3. Okay?
Yay!